All right. Good evening, everyone. Okay, guys. So this is lecture 2, continuation of basic elasticity, what we did yesterday. So, all right. So without wasting any more time, we have seen and started with basic elasticity. And if you recall, yesterday we have seen which is known as stress tensor. So you have seen it for a 3D stress system. You have seen it for a 2D stress system. What are stress unknowns? And we have written this in matrix form for a 3D stress element and for a 2D stress element. All right. Now, today's lecture, our major concern or topic will be to understand what do you mean by principal stresses. All right. This is the major portion or the major topic of basic elasticity. The rest, all things are useful or helpful to calculate these quantities. And these principal stresses will be used in theory of failures to design any system. All right. So before going into principal stresses, I will like to do a topic which is known as stress transformation, and a special case of which will be principal stresses and what is a principal plane. So we will try to understand why we are calculating principal stresses, how we're going to calculate it, what is the procedure to convert or solve any numerical if they ask us to calculate principal stresses, and so on. So first I'll talk about is what is known as stress transformation. All right. This keyword is actually mentioned in your syllabus. So we need to understand this first of all. What do you mean by stress transformation? And I have seen people asking this doubt that why we cut this plane and so on. So it works in this way. All right. So I'll do this derivation. It will not take more than 10 minutes, 10-15 minutes. After that, if I derive principal stress equations, it will be very much easier for you to understand and relate what we have done. If I directly give you a formula, you will be learning the formulas, but you don't understand the concept then. All right. So I'll take our 2D stress system. We will see how to solve for 3D stress system also. And I'll give you two methods to solve any of the numerical. So let's say this is our Cartesian coordinate system in 2D. So you only have X and Y, and you know how a stress element looks like. So if you talk about a 2D stress element, it looks something like this. All right. And you know also the stresses acting on the system now. So there are 3 stresses, 2 normal stresses, sigma X. Now sigma XX or sigma X is one and the same thing. Sigma Y. All right. And we have seen shear stresses are complementary in nature, meaning on 2 mutually perpendicular planes, they are equal and opposite. So if this is shear stress, let's say tau xy or sigma xy, you can write anything. On a plane perpendicular to it, it will be exactly same tau xy and in the opposite direction. Similarly, if I'll see here, something like this and something like this. So I've not written tau xy everywhere because we know this is one shear stress only which is present everywhere. So this is also tau xy, this is also tau xy, and this below one is also tau xy. This is a typical 2D stress element. Now, what we do in stress transformation, guys, please try to understand this. I'm going to cut this stress element. Now, keep this in mind, this body is in equilibrium. All right, this body is in equilibrium. I'm going to cut this stress element at this angle. Now, please listen to this carefully. And I'm going to assume that the angle it is making from vertical is theta. This angle is important because they most of the times will give you angle with respect to horizontal also. Then we need to use trigonometry and calculate angles with respect to vertical. So when we are deriving something, we need to recall our derivations. And then the formula will be corresponding to this. If you calculate angle with respect to horizontal, your equations will be different then. So we'll be deriving everything with respect to vertical now. All right. And after doing this, I'll simply name this triangle. So let's say this is A, this coordinate. All right. Let's say this is B, and let's say this is C. So what I've typically done, I have a 2D stress element which is in equilibrium. And now, guys, I'm zooming this triangle. So if you see, we got this triangle. On this triangle, if you see the below face, this is sigma xy. This is tau xy. This is sigma x. This is tau xy. And now you don't have this right-hand side upper triangle, correct, right? Now, can you please tell me, yes or no, is this triangle, and this angle is theta, is this triangle or this element which we got, is it in equilibrium or is not in equilibrium? I hope you understand this is not in equilibrium now, because you don't have anyone on the right-hand side to keep this body to stop moving, and you don't have anyone on the upward side. So this body is not in equilibrium. But we know all structures should be in equilibrium, right? Static equilibrium should always be achieved. So the plane on which we don't know what is happening, we're going to assume, let's say on this plane, there is a stress sigma n acting. We don't know what the stress is, which is perpendicular to this plane now. No longer we are in Cartesian coordinate. We have cut the plane at an angle. And I'm assuming that, let's say there is some shear stress on this plane, which is tau. So if you see, I have not given any suffix to tau because we don't know which plane is this. This plane can be theta equals to 20 degrees, 45 degrees, 80 degrees, anything. So we have two unknowns present here, which is sigma n and tau. And the stress transformation topic is this. What this topic says, if you know your 2D stress system in Cartesian coordinate, that means xy, you know sigma x, sigma y, tau xy, you know your 2D coordinate system. And if someone says, I don't like this coordinate system, you please give me answers or stresses in some different coordinate system at different orientation. People sometimes say we don't cut it. What they do, they draw the stress element like this. If you see this black body, they have rotated. This is another way of seeing this. Now the question is, what is this stress? What is this stress? It will not be equals to sigma x, sigma y, because it is not going in x direction. So simple transformation meaning is, if you have some stresses in some coordinate system, and if you want to rotate your body, cut your body, change the coordinate system, how your stresses will be calculated and how they will be different. Please give me a quick nod. Is this fine for everyone? Believe me, you will be very good once I'll derive principal stresses in this. All right, perfect. Now what I'm going to do is I'm going to do a method which is not mostly given in the textbooks, but it is a very renowned method. So very simple method to understand. And don't forget that this coordinate was A, this coordinate is B, and this coordinate is C. You need to bear for 10-15 minutes. Once we have the equation, you will feel good that what is the meaning and why we have done this. I'll show you a numerical also that will even make you feel even better what equations we have done and why we are doing this, why this stress transformation is needed. So what I'm going to do, guys, I'll draw a force polygon here. All right. Now, what do you mean by force polygon? A force polygon looks something like this. So you have a vertical axis, which is our y-axis. You have a horizontal axis, which is x-axis. Now I'm drawing two additional lines here. Guys, please stop me at any point whenever you feel you have a doubt. What I'm doing is I'm drawing a line at this orientation. So simply, I'm just drawing a line like this, which is where sigma n is going. And if you people agree, perpendicular to it, there is also a line where tau is going. So something like this. I've simply drawn some lines now. Now let's see some angles. If you people agree, can I say this tau line, this one, from vertical, it is making angle theta, correct? So this line, which is tau line from vertical, it is making angle theta. And now we know all angles between two lines are perpendicular 90 degrees, right? You can see these two are at 90 degrees, these two are at 90 degrees. So everyone is at 90 degree. So if this angle is theta, this angle will be theta. Next remaining angle will be 90 minus theta, which I'm not writing. Then this angle will be theta. And then this angle will be theta. So as of now, I have not done anything fancy here. I've drawn 4 lines, which I am interested in, which was present in my diagram. And I have marked the angles. Now what we do is, you see the name is force polygon, right? All right. So I will be calculating forces in these directions. So now we will do this. Can you tell me what is force in this direction? See, stress is sigma x. Stress into area is force. All right. This sigma x is acting on length AC. And because we are talking about 2D surface, so we are assuming depth is 1. All right. So area or force becomes stress into area. And I hope you people agree that it is acting in this direction. And force acting in this direction is sigma x. I hope it was AC. AC into 1 to be very precise. Similarly, I'll just quickly mark all the forces now. So this is one force. There is another force acting in this direction only, which is tau xy. Now this stress is acting on face BC multiplied by 1. So this is also one stress, which is tau xy, and it is multiplied with BC going in this direction only. All right. Now I'll mark another stress. Let's see this one now. Sigma y into BC into 1. It is going down. Sigma y multiplied by BC. This is force polygon, right? So I cannot mark stresses. I'm converting this into force. Similarly, if you see this is tau xy again, but it is acting on face AC going down. So this is tau xy acting on face AC into 1. So I've marked all my 4 stresses, but there are 2 more stresses acting here. This is one stress, which is sigma n, acting in this direction on face AB. Correct? So this is sigma n into AB. And last stress, excuse me, and last stress is tau, acting on face AB going in this direction. So this is tau acting on face AB going in this direction. Please keep this in mind. When this problem starts, we already know what is sigma x, sigma y, tau xy. And the problem says, if you want to calculate stresses on a plane at certain angle theta from vertical, what is the way how you will calculate? So I'm deriving those formulas now. I hope you people agree. I have up till now done only the force polygon. Now what we're going to do is, please help me. I'll write this equation now itself. Resolve all the forces in this direction. So my first derivation is resolving forces in this direction. All right. So what is the first force? Sigma n into AB. This is one force. Now, if you people agree, and you can say yes or no, if you don't follow, please ask your doubt. Can I resolve this force, which is sigma x into AC, in this direction as a cost component? And I'm writing it, just see if it is fine. Minus, because if you're taking this stress upward, it is going in the opposite direction, minus sigma x into AC cos theta. Exactly similar way, this tau xy BC, which is the force, can be resolved along this line as a cost component alone, and tau xy into BC cos theta. You will not learn this derivation for your GATE, but you will understand every bit of it, and believe me, you will feel good once this derivation is over. Now, what are the remaining forces? This tau xy, if I'll resolve along this line, and I hope you people agree, this will be sine theta term. So minus tau xy into AC into sine theta. This is one term. And now this sigma y BC also resolved in this direction. So minus sigma y BC sine theta. And this tau xy AB need not to be resolved because it is exactly perpendicular to it, right? Is equals to 0. So I have simply resolved simple cost. You do f cos theta, f sine theta, right? If you have a force vector F making an angle theta, this is f cos theta, and this is f sine theta. Same concept I've used here. Now, once we have this, what I'm going to do is, this is simple plus and minus now, guys. I'll keep sigma n on one side, send all the terms to right hand side and divide this equation with AB. I'm doing this in next slide. Please see if it is fine. So sigma n is equals to, I'll send all the terms now. So sigma x AC cos theta, sigma x into AC cos theta divided by AB. Why divided by AB? I'm also bringing this AB to denominator in one step only. Next, I'll write this term. So plus sigma y. What is this? BC sine theta. So this is BC sine theta divided by AB plus, now you see, tau xy into BC cos theta. So plus tau xy into BC cos theta divided by AB plus, last term is tau xy AC sine theta divided by AB. So nothing new. I've taken left-hand side terms to right-hand side and divided this entire equation with AB. How we got this equation? I've simply resolved all these forces along this line, along sigma n line. So I got this expression and I've written this in better form. That's it. Now, if you people agree, what is this AC by AB, BC by AB, all these terms? If you recall your triangle now, can anyone tell me what is this? Yeah, we can check here. What you want? AC by AB, right? What is AC? AC of this triangle is base. Correct? Just check it. Yes, yes, yes. AC by AB, right? I'm just going to that sides now. So AC, which is base divided by hypotenuse, which is AB of this triangle, is sine theta, right? Sorry, cos theta. I'll write it here. Base divided by hypotenuse is cos theta, and perpendicular divided by hypotenuse is sine theta. Correct? Yes, everyone agrees on this. So I can simply do this now. Sigma n is equals to sigma x. I hope you understand this becomes cos square theta plus sigma y sine square theta plus, and I hope you understand this. This is tau xy. BC by AC is sine theta. So this becomes sine theta cos theta. Second term also becomes sine theta cos theta. So I'm simply writing this as 2. Last step. I hope you people agree that this 2 sine theta into cos theta is nothing but sine 2 theta. And many of the books write this as one formula to remember. I never use this formula. I'll give you the another type because in the end, we need to study Mohr circles also. So I will try to keep all my equations in one format. But this is one formula for calculating normal stress on any plane at an angle theta. And if you know your actual 2D stress element, you can calculate this sigma n at any angle theta. So how the numerical comes in your exam, I'm not solving this. I'm just showing you the reason, because you should know what is happening in your, I hope you can imagine. This question is asked in 2019, guys. If you precisely see this, right, you know what is sigma x, you know what is sigma y, you know what is tau xy. They have asked what is the normal stress on a plane inclined at 45 degrees to the x-axis. So if you see, they're asking this sigma n for 2 marks in your exam, for 1 mark. This is question number 24. So this sigma n need to be calculated at an angle of 45. But if you use this equation in your exams, you will get marks, luckily. But don't forget that this angle is 45. So luckily, this angle is 45. So we got the same answer. I hope you understand that why I am trying to make you understand what do you mean by stress transformation. All right. So we will solve all the numericals I already told you. We'll start with 2007 and go till 2023. So this is one equation. Now, the another way of, which is what I can say, more better way of writing this, because further it will be useful when we talk about more circles and all. And this is just trigonometry. You can say this as equation 1 or A. Is it fine if I can write cos square theta as 1 plus cos 2 theta? See, this is 2 theta, right? So what we are doing is, this is theta here, this is theta here, this is 2 theta here. So people don't like this. What they do is they convert everything into one format. We know this can be written as 1 plus cos 2 theta divided by 2. Again, it is helpful in future when we develop equations. This is 1 minus cos 2 theta divided by 2. And this term is as it is. Now I'm writing final formula, which I expect everyone to memorize after this. Where it is? They're forming zero sign due to sign conventions. Where it is zero? Where it is negative, Dilip? I don't understand your doubt. And now in last step, I hope you people agree. I can simply write this sigma x and sigma y plus, so sigma x plus sigma y divided by 2 is my first term, plus, if you agree, sigma x by 2 minus sigma y by 2 into cos 2 theta. I'm writing it. Anywhere you feel you have missed the maths part or any step, then I can repeat it, plus tau xy sine 2 theta. I really emphasis on this, guys. This equation should be memorized. This is the equation which will help me to solve many of my GATE numericals. Is it fine? Is it clear? I need your response in this, guys. This is only one formula for calculating stress on any plane, whichever plane they ask, if I know my conventional 2D plane. Yes, Dilip, it is sign convention. I hope you are talking about this plus and minus, right? See, if you are saying, if this is purely your assumption, if this is going upwards, then anything coming down should be with a negative sign, right? If you want, you take this as negative and opposite should be plus. It's something like this. Fine, good. Now, next part will be very easy for you people to understand. I'll remove this because you people have already written this. And Dilip, I hope this will be even clear for you once I'll write this equation. Now what I'll do is I'll repeat the exactly same step. I repeat exactly same step for tau xy. In this direction, we're going to resolve this. So Dilip, this is purely my assumption that I'm taking this stresses going this direction or right hand side as positive. If you want, take it as negative. Your equations will not change. So I'm saying tau into AB is the stress which is going down. Now I need stresses in these directions. Now can anyone help me? Can I say this sigma x, this sigma x will be resolved in this direction as sign component with a negative sign. So I'll apply minus sigma x AC sine theta. I'm assuming it is clear because we have done the derivation first. So I'm moving bit fast. Similarly, I'll resolve this tau xy in this direction. Again, it will come with negative sign. So minus tau xy into BC sine theta. Fine. Now, if you see these two stresses, this will be resolved in these directions as cos component, but it will be resolved like this, right? So it is going along with our sign convention. So plus tau xy AC cos theta plus sigma y BC cos theta, and they should be balanced out. Then only my body will be in equilibrium. So same four stresses but they are resolved with different cos and sine components now, and with our corresponding plus and minus sign. I'll repeat exactly the same process. What we'll do, I'll keep tau on this side, send all the terms on the right hand side and divide it with AB. Let me do it. So tau is equals to, let's see what we have now. So we have sigma x AC sine theta, sigma x AC sine theta divided by AB plus what we have now tau xy BC sine theta, BC sine theta divided by AB. Next term. Now this term will go on the right hand side with the negative sign. Minus tau xy AC cos theta minus tau xy AC cos theta divided by AB. And the last term is sigma y BC cos theta with the negative sign. So minus sigma y BC cos theta divided by AB. Correct? Now, same step, guys. I hope it is not anything new because we are repeating the same thing for in different direction. You know what is this? AC by AB, right? I have already written it there. What is AC by AB? Cos theta, and BC by AB is sin theta. So this is sigma x, correct. Cos theta, sin theta. I'll write sigma y term first here. This is again cos theta, sin theta minus tau xy. What is BC by AB? Sin theta, right? So this becomes sin squared theta, and this becomes cos squared theta. Guys, is this fine? Clear for everyone? Correct, right? Now the next step is again pure maths. I again repeat this. Don't worry about how these derivations, or you should remember, no, for your gate, you don't need the derivation. But believe me, guys, you will see that you will be so good in structures after doing this small derivations. Whenever it is needed, I'll give you a derivation. Whenever it is not needed, I'll skip it and give you the formula, because in the end, you should understand and solve numericals. Both things should go parallelly within a given amount of time. So it should not be like I should take this lecture for 1 year. It doesn't make sense. So depending upon the topic, I will go in detail whether it is needed or not needed for a derivation. Now, I'll do the last step. I hope you agree. Cos theta, sin theta, if I take common and multiply and divide by 2, 2 sin theta cos theta is sin 2 theta, right? Correct. So I can write this as an agree. Guys, yes or no? Oh, yeah, correct. This is plus. This term is plus. Sorry, I missed it. This term came from here, right? This is plus. Now in next term, if I take tau xy common, and I'm writing this in one step only. If I take tau xy common in these two, I will get this. I'll take minus tau xy common. In bracket, I'll get cos squared theta minus sin squared theta. What is cos squared theta minus sin squared theta? Cos 2 theta, right? So I'll get simple this formula. And this is the second formula which we should remember. For me, I'll remember this as first and this as second. But if you like, you can go with the first equation also. These two formulas, if you precisely see these equations now, if you know sigma x, sigma y, and theta, you can calculate shear stress acting on any plane, whatever theta maybe they have given. And if you know sigma x, sigma y, and theta, tau xy, you can calculate any normal stress acting on the plane. So we got two important formula. No need to worry about the formulas because so many numericals will be solved. You will automatically remember this. But as of now, for this content, stress transformation, is it clear in your mind how we're going to calculate stresses? If I know my stresses in X, Y, and Z direction, X, Y directions, and if you want to calculate in any other plane at any other angle, how you will use the formulas. Is it clear, guys? Everyone, give me a quick nod, because next heading is principal stresses, which will you understand and like a lot. Perfect. Good, good, good. Yeah. Okay. Now, guys, there are so many ways of deriving this, right? If you understand the theory I'm trying to explain, believe me, you will feel good. All right. Now, I'll talk about principal stresses. And principal plane. Now, first of all, I'll give you a theory. Please understand this. This is 90% of your GATE numericals. So this will come in your exam. There is no way they can frame a question paper without calculating principal stresses. You have to calculate it. Now, what are principal stresses? I'll give you the definition first. Principal stresses are normal stresses. All right. Correct. These are only normal stresses. These are not shear stresses. Principal stresses are normal stresses, which are either maximum and minimum principal stress, maximum and minimum normal stress, acting on a plane where shear stresses are zero. Now, please listen to this carefully, what I'm trying to say. This is only for your understanding. If you have a stress system, something like this, guys, believe me, no one will explain you this concept, because directly you have a formula. All right. And there are some shear stresses. Now, what I want you to understand is, let's say I don't like this. I want to, now from where this stress element is coming, this stress element is coming like this, guys. You have an aircraft, all right, which is having an aircraft wing, and you want to analyze whether your aircraft wing will fail or it will pass or it will not break. So what you do is you take a small element from here and then zoom it. That's what the 3D stress element is. But in reality, you will cut 3D stress element, right? As of now, we are analyzing 2D stress element. We'll see there are different elements, plane stress, plane strain. But what if someone says, I don't like this, you cut it here and you have calculated sigma X, sigma Y. What if someone comes and cut it like this? Or what if someone comes and cut it like totally different orientation? So it is up to engineer where to cut, but as an output, as an engineer, whatever you cut, it's fine. My major intent is to tell me where you're having the maximum stresses. Now, what I'm trying to tell you is, someone comes and cut this 2D stress element like this. So there will be two normal stresses like this, two normal stresses like this, and there will be one shear stress. Now, the thing I want you people to understand is this. Is this stress, guys, say yes or no, is this stress sigma X? Yes or no? Come on, guys. This is not sigma X, right? Why? Because it is not going in X direction. So because I've always seen people understand this in better way if I give numbers to it. All right. So let's say in first, sigma X value here in first case was 20. Sigma Y was 20. And tau XY was, let's say, 10. I'm just giving you an example, hypothetical example. Yeah, possible. Yes, Tushar, yes, you can do it. But now when you rotate it, you don't know the value, right? So I'm giving you hypothetical numbers. Let's say when I rotate this sigma, this stress came out to be, let's say 25. I'm just again telling you, giving you some hypothetical numbers. It depends upon angles now. Let's say this becomes 15 and this tau xy becomes 5. You did some calculations, maybe cos theta, sin theta, apply equilibrium equations, whatever. How you will do in reality? If you see, this is angle theta plane, right? This we have already learned. If I know stresses in x, y, and z direction, x, y, and tau xy, and if you want to calculate stress at an angle theta, you can do it. Now, this is an application, guys. If you see this plane, which I have marked in red, is at an angle theta from vertical, right? So if you know sigma x, if you know sigma y, you know tau xy, you can use that equation to calculate this and this. It can be solved. Is it clear, Tushar? This is beautifully framed, guys. Believe me, this is a very good application of why we calculate stresses at certain angles. You can calculate this. Let's say someone says, guys, is this clear for everyone? I need your responses in this because this is not basic. This is core structures. You have to understand this. All right. Now what I'm going to do is in next case, let me rotate it even more. Now this stress will be different. This stress will be different. This will be different. This will be different. Now what, when you have calculated, and this angle is some different theta from vertical. Now when we have done this, right, unknowingly, I came to know that this stress was, let's say, came out to be 30. This came out to be 10. And luckily, there was no shear stress. Shear stress was 0 here. This is the plane. This is the plane on which there are no shear stresses. Normal stresses will go to maxima and minima. So there are two principal planes. The two principal planes are always at 90 degrees. One principal plane I have shown in blue. Another I'm showing in black now. This one. So principal plane is the plane at which there are no shear stresses acting. And the corresponding normal stresses will be maxima and minima. That plane, what is this plane? This theta is known as principal plane. And the normal stresses, which is 30 and 10 here, are known as major and minor principal stress, bigger and smaller principal stress. What I'm trying to tell you is, guys, you can rotate it. There are infinite possibilities. Now, I don't want to do infinite cases. I want you to tell me what is the angle of theta if you rotate or you cut the body. Your normal stresses will go to maximum. That plane is known as principal plane. And the definition is that on that plane, your shear stresses are 0. Do you understood what do you mean by principal stresses and principal plane? Now, okay. So question asked by Tushar is, what is the use of finding principal stresses? So Tushar, do you agree that maximum principal stress, maximum stress is what the intent is should always be? See, this 30, I have tried to give in the number so that you can understand. If you see here, stress is 20-20. Here, stress is 25-15. This 30 is the maximum stress where no other stress can be bigger than this. That is what is principal stress. It is the maximum principal stress and the minimum principal stress. Always when you want to design a structure, you want to calculate maximum stress, right? Maximum problematic zone. That is what principal stress is, right? Do you agree on this? Understood this, Tushar? I hope I have answered your question. The reason of calculating principal stresses are, these are the maximum and minimum normal stresses. So you always want to go to extreme calculations, right? What is the worst thing you can do to a system? Analyze that. If you're saving your system at 30 megapascal, then 25 and 20 is already passed, right? I need not to worry at other orientations. Now, keeping this in mind, if you understood the derivation, if you understood the theory, this you will not find in books. I've just generated these cases so that you can at least relate in your mind what are principal stresses. If you see, they will give you certain definitions. All right. Principal stresses, I'm not writing the statements now, you should understand. If you want to calculate principal plane, now it should directly strike or hit in your mind when someone asks principal plane, right? That person is asking what is theta from vertical. So if you want to calculate principal plane, the best thing to do is on this plane, my tau should be 0, as simple as that. Because what is definition of principal plane? A principal plane is one on which there are no shear stresses, and the corresponding normal stresses will be maximum and minimum, and we name it as major principal stress and minor principal stress. In a 2D stress system, there are two principal planes. In a 3D stress system, there are three principal planes. We're talking only about 2D stress system now, so please focus on this. Now, how to derive this? Now you will understand why I've derived this. On any angle theta, on any angle, let it be, you rotate by whatever angle. If you want to go to principal plane, on principal plane, what should be tau? It should be 0, right? This is the backbone of principal stresses. So I'll simply take my equation, which is any arbitrary equation in terms of theta, and equate it to 0. If you people agree, I'm simply saying this, tau, which is 0, is equals to sigma x minus sigma y divided by 2 sine 2 theta minus tau xy cos 2 theta. You see, I've simply taken this equation and equated to 0. When you equate tau equals to 0, means you have reached principal plane. Now, if I'll solve this again, plus minus, very simple. I'll take this term to other side. Sine theta divided by cos 2 theta is, okay, let me do it. Tan 2 theta. All right. And this term will be, if you don't follow this step, please tell me. I'll do it for you again. But I've simply taken on the other side, formed tan 2 theta by sine 2 theta by cos 2 theta. And if you want to calculate theta here, you got this formula. 1 by 2 tan inverse of 2 tau xy divided by sigma x minus sigma y. Very, very important formula, or I should say only formula to calculate what is known as principal plane. So this is the plane, this is the theta. So if you know sigma x, if you know sigma y, if you know tau xy, you can use your calculators and see at which plane my stresses will be maximum. So even though I have cut it as a 2D stress element like this, I can predict still where my stresses will be maximum without again cutting the system, rotating step by step. No need, not required. But I told you there are two principal planes, right? This is one principal plane, and the other principal plane will be orthogonal to it. So if I know one, I automatically know the other one. Why? You should understand this. So guys, what is principal plane? If I say my body is this angle is theta. If I'm saying this theta 1, this is my principal plane. On this plane, if you apply stresses, you should say this is sigma 1. This is sigma 1. This is my principal stress. On a plane perpendicular to it, there is second principal stress, and you should never mark shear stress. Any plane on which there is shear stress, it is not a principal plane. Any plane in which shear stress is not present, it is definitely a principal plane. So what I'm saying is, what we'll do, we'll calculate theta 1, this plane is theta 1. And if I add 90 to it, I'll get this another plane, which is theta 2. So what is the procedure for calculating principal plane? Again, the backbone is if you know your 2D stress element. This is the reason I asked you to see the video, those who have missed the first one. We should know what a stress element is. What is sigma x? What is sigma y? What is tau xy? And if you know this, you can calculate stresses at any arbitrary plane. You can calculate principal plane, principal stresses. You can do anything if you understand your stress element. So this derivation, what I've done is to calculate the principal planes. Is this clear for everyone? All right. Now, next, this I'm not deriving, although there is a procedure, definitely, but it is not needed because you understood everything. Then it's better to show you this with the help of a numerical. What we need to do is, if I substitute this theta, now this is the theta at which you will have maximum stresses, maximum normal stresses. So this equation is used to calculate theta by substituting tau as 0. And now whatever theta you got, if you substitute in this expression, right, and solve it now, again, it is a long process. I need to substitute cos 2 theta, sin 2 theta from that equation, solve it. Whatever you will going to get will be principal stresses. And now this derivation is not needed, definitely not needed. So the principal stresses, we will denote by 1 and 2. So no x and y now. So whenever your tau is 0, the stresses will be denoted as sigma 1, sigma 2 is equals to, and I really hope at least sometime you have seen this expression, sigma x plus sigma y divided by 2 plus minus under root sigma x minus sigma y divided by 2 whole square plus tau square xy. Best formula in structures to calculate principal stresses. This is formula. I'll give you an eigenvalue method in which formula is not needed. So you can use matrix and eigenvalue properties to calculate sigma 1, sigma 2. And third is Mohr circle method, which is graphical method to calculate again, same thing. So we'll do it step by step. As of now, we are seeing analytical solutions. So big maths formulas we are seeing. Again, I'm telling you how we got this formula. These are the normal stresses. So sigma 1 here, guys. Sigma 1 is a bigger one. So this is major principal stress. And sigma 2 is a smaller one, which is minor principal stress. And if when someone says, what is tau acting here? It is definitely 0. Then only it is principal stresses, right? So this is maximum and minimum normal stress acting on this plane and this plane, which are principal plane where tau xy is 0. How we got this? I have simply substituted this theta value in this expression and have derived this. No, definitely no need to do this derivation, but you should know what principal stresses are. I'll try to sum up all the formulas later, but as of now, you please tell me, is this part clear to all of you? Are these things clear in your mind? Perfect. Good. So what we have understood, we have only understood what are principal stresses up till now. All right. Now, before going into a numerical, which is my next chance, I'll tell you what are different ways of asking a numerical, how they frame a numerical in your exam. All right. So I'll tell you 3 ways. I'm talking about a GATE numerical, how they will frame it. So they will give you a 2D stress element saying something like this data they provide. Sigma X is 100 MPa. Sigma Y is, let's say, minus 50 MPa. And tau XY is, let's say, 20 MPa. If you have this, please calculate what is major principal stress, what is minor principal stress, something like this, or maybe what is principal plane or something like this. This is one way of asking a question, statements. Second question is, they will say, a stress element looks something like this. So can you tell me what is this first diagonal element? This is sigma X. Second, sigma Y. And this is tau xy. And again, they ask me, please tell me what is sigma 1. Please tell me what is sigma 2. Please tell me what is theta. I'm just telling you how to frame same numerical in theory form, same numerical in matrix form. And the third is they don't even do this. What they do, they'll give you the element directly. They say stress acting here is 100. They say stress acting here is minus 50. Now, if I'll say minus 50, I should do this. If you don't want to write minus, you should compress it, apply a compressive force, and then tau is 20. This is third way of asking the same thing. Guys, do you understand the three procedures? All right. Now, I'm not solving because I don't want to waste my gate numericals, but at least you can familiarize yourself. I am not solving this because for this we need Hooke's law, generalized Hooke's law. I just want to show and represent, just to show that what we have done, how is it making sense? So this is question asked in 2008. Again, when we solve gate numericals, right, we will come back to these solutions in the game in a particular sequence. I'm just using it to show that what we have done and how these things are useful. A two-dimensional state of stress in an isotropic material is given by. So don't worry about materials. I'll be discussing about isotropic, transversely isotropic, orthotropic, anisotropic, allotropic. All these materials we'll discuss. As of now, don't worry about these material properties. A two-dimensional state of stress. And if you see, this is one format. Sigma is equals to -8, 5, 16 megapascal, where C is linearly proportional to applied loading. Don't worry. The first question says, what are the principal stresses? So if you understood what I was telling, this is the format, how they're going to frame numerical. So they have given me a matrix. And if you see all the answers in terms of C only, so don't worry about that. So can you tell me, or anyone help me in this? What is sigma x in this, guys? Perfect. It is -8 C. Yeah, multiplied with C, right? One should, it is already given. What is sigma y? It is 16C. And what is tau xy? It is 5C. Correct? So you know sigma x, you know sigma y, you know tau xy, and I just need to calculate principal stresses. There are two ways of doing it. I'm giving you both the methods. Please listen to this carefully. One method is what we have derived. Can you tell me what is the method? If you want to calculate two principal stresses, formula is sigma x plus sigma y divided by 2. I'm just repeating that formula. Under root sigma x minus sigma y divided by 2 whole square plus tau square xy. You substitute all the values, you will get your solution. So Rugma already gave me the answer. What is 5C in this, Rugma? No. We need to substitute the values. So this is -8 plus 16 divided by 2 plus minus. This is -8 minus 16 divided by 2 whole square plus 5C whole square. Sigma 1, 2 is equals to. Now what we need to do is, I'm leaving for you people to do it. Once you take this number plus of this, once take another number minus of this. I'm waiting for you people to respond on this. Can anyone help me? What is the answer? I have this key. I can tell you, but first I want you to tell me, is this fine? So if you solve this, true. Sigma 1, yes, Tushar, is 17C. I got one value along with plus sign. And sigma 2 along with negative sign, I'm getting 9C. Now again, guys, if you don't follow this, please feel free to ask. I will repeat this again. So 17C and sigma 2 is 9C. So I hope you understand that your option is option A. This is asked for 2 marks. I know it is It looks simple once you know the formulas, but you should know how they can frame easy and bad numericals. This is, I'm showing you method 1, which is conventional method. You have a numerical, you have learned a formula, you solve it. You don't use any property out of it. But then next step will be to understand it using properties. Give me a quick nod, guys. Is everyone fine with this? All right. Now, what is method 2? All right. Method 2 is making use of matrices eigenvalue properties. All right. So I'll remove this. I really hope that you have already written the solution. Now, the eigenvalue matrix is this, guys. It will be more detailed when you go into linear algebra and understand matrices and eigenvalues. As of now, I'm giving you what is needed for structures. Property says the sum of diagonal elements. You know what is sum of diagonal elements, right? Sigma x plus sigma y is equals to the sum of your principal stresses. Before that, if I'll give you a simple case, right? If you know any matrix, I'm not saying any in structures, any matrix. I hope you have heard about the term that this 2 by 2 matrix will have 2 eigenvalues. In maths, we denote it as lambda 1, lambda 2. So there are methods to calculate it. If you have a stress matrix, its eigenvalue will be represented as principal stresses. So principal stresses of a stress matrix, if you use this application in maths, any matrix eigenvalues are nothing but principal stresses in our case. What I'm trying to tell you is, in maths, you simply say you have a matrix, please calculate eigenvalues, fine. But now in structures, if that matrix is of stress matrix, right, its eigenvalues will represent principal stresses. Now, what do you mean by this? The property is this, guys, first property. And these are eigenvalue properties, not any structural property. Property says the sum of eigenvalues. Eigenvalues are nothing but our principal stresses in structures. The sum of eigenvalues of any matrix is equals to sum of diagonal elements. This is property 1. Second property, product of eigenvalues. If you multiply these two, it will be equals to determinant of the matrix. Now, what is determinant of the matrix? Sigma x into sigma y minus tau square xy. If you have a matrix sigma x, sigma y, and tau square xy, what is the determinant of this? Sigma x into sigma y minus tau square xy. So if you know, and what is sigma 1, sigma 2, guys? In maths, these are nothing but our eigenvalues. In structures, principal stresses are nothing but our eigenvalues. So if you know these two properties, right, you can again end up with the same solution. What I'm trying to tell you is sigma 1 plus sigma 2 are principal stresses, which we don't know. Sigma x plus sigma y. In this numerical, what are our diagonal elements? Minus 8c and 16c. Sum of diagonal elements. And product of my eigenvalues is nothing but equals to, if you agree, sigma x is minus 8, sigma y is 16, 16 into minus 8, let's say c square, minus tau square xy, which is 5c whole square. You solve these two equations. I really don't want to spend time in explaining you plus and minus. If you have two equations in maths and you have two unknowns, sigma 1 and sigma 2, you can easily use it to calculate. And believe me, you can try this. You will get this as 17c and you will get this as minus 9c. And this is nothing but our eigenvalue approach. So what is the steps to remember, guys? I will use, most of the times I prefer this method, and you will come to know why in the next numerical itself. I'm again repeating this. Sum of principal stresses is equals to sum of diagonal elements. product of ice principal stresses is equals to determinant. Now you can even verify this. Can you tell me which option you got? Option 1, right? Using method 1 also. What is the sum of sigma 1 and sigma 2 in this case? 17C minus 9C. That means 8C, right? And what is sum of our diagonal elements, guys? 8C, right? That means this solution is correct. With this property itself, I can eliminate all the numericals. All the 3 options are wrong. Why? Guys, what is sum of diagonal elements here? Guys, I hope I am making sense. The sum of diagonal elements here is minus 8 plus 16. So I should get 8. And sigma 1 and sigma 2 solution should also be 8. So if you see option B, 17 plus 9 is 26. Wrong. Minus 17 minus 9 is minus 26. Wrong. Minus 17 plus 9 is minus 8. Wrong. 17 minus 9 is 8. So only option which is satisfying my first property itself is giving me the answer. So without touching pen also, you can actually mark this numerical. I really don't expect you people to master this, when to use formula, when to use property. I will solve many numericals of this sort, but please tell me first, is this really making sense? Do you understood the whole concept? Perfect. Good.